Welcome back. In this video, we'll talk about designing the TinyURL service. Now, before we dive into designing the TinyURL service, it is very important for us to understand what exactly it is. So a TinyURL service, also known as the URL shortener service, does exactly what it sounds like. That is, it shortens the long URLs. So here's how it works. You provide a long URL. Think of a long URL as a really long web address. Let's say to a particular page on the internet. For example, something like this. The service takes this long URL as the input and then gives you back a shortened URL. The TinyURL service helps you to shorten these URLs, making it much more easier for you to remember. Welcome back. Now that we understand what a TinyURL service is, let's explore why it is so useful. That is, why do we need to shorten these URLs at the very first place? Firstly, they are very easy to share. Imagine this long URL and then this short URL. Now, trying to share that long URL on social media would be a nightmare. It's cumbersome and prone to errors. But a short URL, it's simple, neat, and much easier to share and remember. Second, character limits. Let's talk about the platforms like Twitter, where every character counts. So this is a tweet with a long URL and this is a tweet with a short URL. Short URLs save space, so you have more room to write your message or even add hashtags, making your tweet more effective. Third, it is clean and professional. Consider sending this email with a long URL and then this email with a short URL. The short URL looks much more cleaner and more professional in emails or documents. It improves the overall presentation and readability, as you can see, leaving a better impression on the recipient. Now that we understand what a TinyURL service is and why it's needed, it's time to think what our service should be able to do. This is where we define our functional requirements. Functional requirements are like the must-have features for our service. They describe what the system should be able to do to meet the user's needs. Let's take a look at our functional requirements for the TinyURL service. First, to generate a short URL, the service should be able to take a long URL as the input and then return a shorter version of it. Why it's important? Of course, this is the core function of the TinyURL service. Without this, we wouldn't be able to create those easy to share short URLs that make the service so valuable. Second, to get the long URL back, the service should take the short URL that it generated as the input and then give back the original long URL. After shortening to a URL, people still need to reach the original web page or the content. This function or this requirement makes sure that the short URL can be turned back into the full original URL, so users can find what they are looking for. Now that we have discussed our functional requirements, let's move to the non-functional requirements. These are the qualities and the characteristics that our TinyURL service needs to have in order to work efficiently and reliably. First, availability. Now imagine if the TinyURL service goes down. Users wouldn't be able to access their original long URLs. This would be frustrating, especially if people rely on those links for important information. So our service needs to be highly available, meaning it should be up and running almost all the time with 99.99999% uptime. Second, low latency. No one likes waiting, especially when clicking on a link. If the TinyURL service is slow, users will experience delays in opening the website, which can be annoying. Therefore, it's essential for our service to have low latency, which means it should respond quickly to the user requests. Third, scalability. Our service should be ready to handle a lot of traffic, especially since it will be used to create short URLs for many web pages and be used by millions of users. We definitely expect large-scale usage. So, the system must be scalable to manage high traffic efficiently without any issues. Now that we have defined our functional and non-functional requirements, it's time to move on to the capacity estimation. First, let us see the estimated number of users that our service should be able to support. We'll begin with estimating the daily active users, or the DAU. The daily active users refers to the number of unique users who interact with our service on a daily basis. For our TinyURL service, we estimate this to be around 300 million people. Second, monthly active users. Monthly active users refers to the number of unique users who use our service over the course of month. For our service, we estimate this to be around 1 billion people. Now, estimating users is the very first step in capacity estimation. This is because everything starts with understanding the users. Imagine you are planning to build a restaurant. Now, before you decide on the space, the number of floors, or how many tables you need, the very first thing that you need to figure out is how many people will visit. Once you know that, you can make informed decisions about everything else. Now that we have estimated our user base, let's move on to calculating the throughput, specifically how many read and write requests our system will handle daily. According to the functional requirements, there is only one primary way to write data into the system. That is when the server creates a short URL for the given long URL input from the client. Let's assume that only 10% of our daily active users will create short URLs. Now, with 300 million daily active users, that means 30 million users are creating short URLs daily. Now, let's also assume each of these 30 million users is creating 5 short URLs per day on an average. Therefore, we end up with 30 million users multiplied by 5 short URL requests per day. That amounts to 150 million shortened URL requests per day. Now, this is the total number of write requests or write operations that our system will need to handle each day. On the reading side, there is just one primary operation. That is when the client reads the original long URL back, providing the shortened URL input. Let's assume that all of our daily active users this time will be engaging in this operation. Also, let's assume each user sends 20 retrieve long URL requests every day. Now, with these assumptions, we end up with 300 million daily active users multiplied by 20 get long URL requests per day. This amounts to 6 billion get long URL requests each day. This is the total number of read requests or read operations that our system will need to handle each day. Let's now move to the storage estimation. When the user sends a request to create short URL, a short URL to long URL mapping is created on the backend. Now, the size of this mapping can be estimated to 100 bytes plus 30 bytes plus 70 bytes. 100 bytes, the average size of a long URL, 30 bytes, the average size of a short URL, and 70 bytes for additional metadata like timestamp and user info. So this amounts to 200 bytes. And from our throughput estimation that we did in the last section, we saw that there are 150 million create short URL requests per day. Therefore, the total storage per day would be 150 million create short URL requests per day multiplied by 200, which is the average size of a short URL to long URL mapping. This amounts to 30 gigabytes of storage per day. So the total storage required in 10 years, naturally, it would be 30 multiplied by 365 multiplied by 10. This would amount to 109.5 terabytes of data. Welcome back. Now, let us estimate the memory. When I say memory, I am referring to the cache memory. Why cache? Accessing data directly from the database can be slow. So to speed things up, we use a cache, which is a faster type of memory where we store the frequently accessed data. How much cache? We calculated that our system will need to store 30 gigabytes of data every day. Now, since 30 gigabytes isn't a large amount, we can store all of this data in the cache, making it quicker to access. As our system grows and handles more data, our cache memory needs to grow too. This ensures our service remains fast and efficient even as the amount of data increases. Next, let us estimate the network and the bandwidth. Effectively, we want to figure out how much data flows in and how much data flows out of our system every second. Let's take a look at the data flowing in. It is also called as ingress technically. This is the data that enters our system every second. Now, we already know that the total amount of data stored in a day is around 30 gigabytes. Therefore, the data flowing in our system every day is also 30 gigabytes. To find out how much data comes in every second, we divide this number by the number of seconds in a day. So 30 gigabytes divided by 24 hours into 60 minutes into 60 seconds. This amounts to 0.35 megabytes per second. So the ingress, which is the data entering in our system per second, is 0.35 megabytes. Next, let us estimate the data flowing out, also called as the egress. Now this is the data that leaves our system every second. This happens when users ask for the long URL from a short URL. So effectively, whenever we are reading the data from the system, that is precisely when the data is leaving from our system. We have 6 billion read requests every day, as we saw in the throughput estimation. Now each request returns about 200 bytes of the data. We saw that 200 bytes of the data is the average size of an entry in the database. So to calculate the outgoing data, we'll have to multiply 6 billion requests multiplied by 200 bytes. This amounts to 1200 gigabytes per day. Now to find out how much data leaves our system every second, we just divide this number by 24 hours into 60 minutes into 60 seconds. This would amount to 13.8 megabytes per second. So 13.8 megabyte of the data leaves our system every second. Welcome back. Let's now take a look at the API design for generating a short URL. You can think of an API as a way of communication between the client and the server. So when we ask the server to shorten the long URL for us, we are effectively using an API call. Now on a super high level, this is how it looks. We have the client here. He has a long ugly URL. He clicks on the shorten button. As soon as he clicks on the shorten button, then an API request is sent to the TinyURL service. On a super high level, this is saying, hey TinyURL service, can you shorten this ugly long URL for me? Now if we dive deeper into the technical details of this communication, this is what is happening. We have the HTTP method as post. What is an HTTP method? Simply, it's just telling the server what action it needs to do. So when we ask the server to shorten a URL, we are asking it to create a short URL for the long one that we give. Now because we are asking the server to create something for us, we are using post action. Second, we have the endpoint. This is telling the server where we need to perform that action. Now since we are creating a short URL for the long URL input, we will use v1/urls endpoint of the server. v1 means version 1. It's a good practice to version your APIs. Another example to understand all of this. Let's say you want to design an API for creating a new user account. What would be the HTTP method you would use and where you would perform that action? Think for it for a moment. You got it right. You would use post, which is what action, because we want to create an account. And then where to do, we would use v1/users endpoint because we are creating a user account. So this is the target. Next, we also have the HTTP body. Now we have told the server to shorten the long URL, but we haven't told which URL to shorten. Now this information is sent in the request body. Now let's look at the other side of the picture. That is, how can we get the long URL back with the short URL? We zoom into the communication or this particular API. We'll basically use again a REST API for this. On a super high level, this is how the flow is. You type in the short URL in your browser and then you hit enter. A request is sent to the TinyURL servers. On a super high level, it says, hey TinyURL service, can you please give me the original long URL back for the short URL? The service gives you back the long URL and then that long URL is redirected to the web page. Now what HTTP method and what is the endpoint? That's the question. The HTTP method is get. It's quite simple because we are getting the long URL back from the provided short URL input. The endpoint that we use is nothing but the short URL itself. This is because this is the endpoint that we type in our browser. Also, the GET requests do not include a body because they are used to fetch the information. So there is no need to send any data. Let us look at the end-to-end flow when a short URL is actually generated on the backend for a given long URL. So the following steps are involved sequentially. First, when a user tries to shorten a long URL, first a request is sent to the backend. This request is sent to the TinyURL servers and would be a post request. This post request would contain the long URL input that the person wants to shorten in the request body. This is what we saw exactly in the API design section. Then after this, the request would reach the API gateway. This API gateway would be the entry point for all the requests to our TinyURL service. It would handle this request, perhaps would validate that, authenticate that, authorize that, and then ultimately it would route it to the generate short URL service via a load balancer. Now this generate short URL service is the core service that has the main business logic to actually generate the short URL for our long URL. So it would take this long URL as the input, run some code, generate a short URL, and then ultimately save this mapping of short URL to the long URL in the database. We call this database as the URL mappings DB. We also store this in the cache, the URL mappings cache, just for faster access if needed. Ultimately, the generated short URL is returned back to the client. Welcome back. Let's now move to the next section where we'll discuss a fundamental problem that may occur in our design if we are not careful. I'll begin with an example. Let's say a user comes and submits google.com as their original long URL. The system processes that, generates a short URL called as tiny.url/abc, and then this is returned back to that user. Now that user again comes and submits facebook.com as his original long URL. He wants to get a short URL for Facebook this time. The system processes that, generates the short URL again as tiny.url/abc. Now, this situation is effectively called as a collision. As you can see in the table, that both the Google and Facebook are mapping to the same short URL. Now think about it. What would happen if a person or that user precisely tries to open tiny.url/abc? Would it open Google? Would it open Facebook? It leads to confusion, right? So let us see how we can solve this problem and prevent it from happening. Welcome back. So how do we make sure that there are no collisions? Collisions happen when the same short URL is generated for two or more different long URLs. To avoid this, our short URL generator must always create unique random strings. Now you might ask, how can we achieve this? Well, there are many algorithms available that can generate random strings. These algorithms are designed to create a new unique string every time they are run. So no two strings would be the same, which ensures that there would be no collisions. But it's not that simple. Here's the catch. If we run the same random string algorithm, but on two different servers, it cannot guarantee uniqueness anymore. Why? Because these servers don't know about the strings generated by each other. This means there's a chance they could generate the same string, leading to collisions again. Now because of this, we cannot use the random string generation approach to avoid collisions across the multiple servers. Let's look at another approach. Earlier we learned that using random string generation on different servers led to collision problem, where two different long URLs could end up having the same short URL. Now to tackle this, let's use a smarter method, an algorithm like MD5. So how does MD5 help? MD5 create unique outputs, not based on the servers, but based on the input. So if the input passed is different, irrespective of the server where the algorithm is run, the output will be different. So if we input two different long URLs, MD5 will guarantee that each will have a unique output, meaning no two long URLs will ever get the same result. Have we solved the problem? Not yet, but here's the catch. While we can say that MD5 generates unique strings, but it outputs a long string that is more than 20 characters. That's too long for our needs, for the need of generating a short URL. So can we shorten the MD5 output? Yes, a quick idea would be to take the first 7 characters from the MD5 output and then use that. But here's where the problem creeps in. While MD5 guarantees that the whole string is unique, it does not promise that the first 7 characters will be unique. As you can see from the diagram, if we take only the first 7 characters, a collision can still happen. 2 different long URLs could end up with the same short URL, even though their full MD5 strings are different. So unfortunately, this approach also doesn't work. So in the previous approaches, we tried different methods to avoid collisions when generating the random short URLs. But collisions still occurred, and those methods weren't enough to prevent them completely. So let's try something different this time. Let the collision happen, and then handle it afterward. So how does this work? When a new long URL comes in, we generate a random string like usual. If the random string doesn't cause a collision in our database, we just store the short URL and long URL mapping like we usually do. But if the random string does cause a collision, we generate another random string and check again until there's no collision. Let's take an example. As you can see in the diagram, Google generates 14JS MC9. No collision, add it to the DB. Facebook generates ANG983M. Again, no collision, add it to the DB. Instagram generates 14JS MC9. It's a collision. Now in this case, Instagram generated the same short URL as Google. So we need to run this algorithm again and generate a new random string. Let's say SUCHR71 this time. Now this doesn't collide. We just add this new mapping to the database. Does this solve our problem? Yes, it does. But it also introduces another problem. What is that? Every time a collision happens, we need to check the database and try again. Now this thing takes time. You can imagine as our system scales and more users generate short URLs, the chances of these collisions happening also increases. And then we spend more time checking and regenerating. So this would make our system slow in the context of high scale. Also, it goes against our requirement of low latency. So can we use this approach? No, because the system becomes slower as we generate more short URLs, and we need a fast solution as per our non-functional requirement. Now, so far we have seen that using random string generation led to collisions. And we have also seen that when we regenerated strings to avoid these collisions, it led to another problem that was of introducing the latency. So, what can we do to solve this? How about if we can just eliminate having collisions or avoid having collisions entirely, without needing to regenerate the strings? I'll start with the simple approach, a numbering system. For example, google.com. Let's generate tiny.url/1. Effectively, we are giving the number 1 to Google. Facebook.com. Let's generate 2. Instagram.com. Let's generate tiny.url/3, and so on. Now, by assigning a unique number to each of the long URL input, we can definitely guarantee that there would be no collisions, because every URL is bound to get a distinct number in the sequence. It's simple and effective. However, there's a catch. If you run this algorithm independently on different servers, the same issue arises. Each server starts generating the numbers from 1, 2, 3, and so on, without knowing what numbers the other servers are assigning. This leads to collisions again. Now, to solve this, we need a way for all the servers to coordinate with each other. By coordinating with each other, they will ensure that they don't generate the same numbers or there is no overlap. Now, how can we achieve this? This is where precisely the Zookeeper comes in. Zookeeper solves the problem of coordination between distributed systems, in this case between these distributed servers. Zookeeper will ensure that these servers can coordinate to assign unique numbers, preventing collisions. Effectively, it would give a different range to each of these servers, and therefore it would prevent any overlaps from happening. Interested in learning more about the Zookeeper? Let's dive into the next one. Welcome back. Now in this video, let us understand what the Zookeeper is. Now as we have seen that Zookeeper would help to coordinate between all of the servers to make sure that there are no collisions in the generated URLs. Now how does this happen? Each server, as you can see in the diagram, would be connected to the Zookeeper service, and Zookeeper service would be able to communicate with all of them. Now every server would ask the Zookeeper for a range of numbers. Zookeeper gives each server a different range to avoid the collisions. The server then uses this range to generate the numbers one by one. For example, server 1, as you can see in the diagram, gets the range from 1 to 1000. Server 2 gets the range from 1001 till 2000 from the Zookeeper. Now in this way, we can ensure that every server would be getting a unique range, hence avoiding any collisions altogether. In this way, the Zookeeper would bring coordination between all the servers and solve the collision problem completely. Alright, so we have already looked at how the Zookeeper helps servers coordinate by sending a unique range of numbers to each of the server to avoid collisions. But now let's take this further and figure out how can we generate even shorter URLs without increasing their length over time. Right now, our URLs follow a simple numbering system like this: tiny.url/1, tiny.url/10, tiny.url/1000, and it goes on similarly. But as we keep going, the length of our URLs grows. Precisely the length of our short URLs, they become longer. So they start looking less short. So what can we do to keep the URLs short while still being able to generate a ton of them? This is where the base 62 encoding comes. Now currently, each digit in our URL is based on base 10, meaning each character is a number between 0 and 9. But what if we get creative and expand the number of characters that we can use? Let's include numbers 0 to 9, uppercase letters A to Z, and lowercase letters small a to small z. So we have a total of 10 plus 26 plus 26, which is 62 possibilities. That is exactly base 62. It's like giving our numbering system a major upgrade. Why is this useful? With base 62, instead of generating URLs like tiny.url/1, tiny.url/2/100, goes on till tiny.url/9876549, let's say. Now this is base 10. With the help of base 62, we can create much shorter URLs that represent the same numbers. For example, 9876549 in base 10 becomes FRLB in base 62. I'll bring that down for you. So in base 10, we have 9876549. This is written as 9 into 10 to the power 6 plus 8 into 10 to the power 5 plus 7 into 10 to the power 4 plus 6 into 10 to the power 3 plus 5 into 10 to the power 2 plus 4 into 10 to the power 1 plus 9 into 10 to the power 0. Now in base 62, the same number 9876549 is written as small f, capital R, capital L, capital B. Each digit can be of 62 characters now. So FRLB in base 62 becomes small f into 62 to the power 3 plus capital R into 62 to the power 2 plus capital L into 62 to the power 1 plus capital B into 62 to the power 0. Now see the base 62 table for reference. How can we get the numbers corresponding to these letters? So this would translate to 41 into 62 to the power 3 plus 27 into 62 to the power 2 plus 21 into 62 to the power 1 plus 11 into 62 to the power 0. This is exactly 9876549. So effectively, what did we do? Using base 62, it helped us to give way more possibilities and combinations for that single character. For example, with just 7 characters, we can generate 62 to the power 7. That is 3.5 trillion unique URLs. Why 62 to the power 7? Because every character can be of 62 possibilities instead of the 10 possibilities we saw in base 10. Now this 62 to the power 7, which is 3.5 trillion, is way more than we ever need for our scale. So effectively, it's all about saving space. By expanding the possible values of each character, we can pack more information into fewer characters. This means we can generate billions or trillions of unique short URLs without having ever to worry about them becoming longer and messy. Now that we have added the Zookeeper and implemented counters, we have fully solved the collision problem. So let's now summarize everything and walk through how our final flow looks. First, when a user wants to generate a short URL for a given long URL, they would first send a post request. This request would contain the long URL in the request body. For example, if the user wants to shorten, let's say sweetquery.com, then he would send sweetquery.com in the request body. Second, the request would reach the API gateway. The API gateway would handle this request, maybe do some validation, and then ultimately would pass this onto the appropriate service, which is the generate short URL service. The request is passed via a load balancer that you can see in the diagram here. Then the generate short URL service would contact the Zookeeper service to get a range of unique counters. Why unique? Because we do not want to have collisions, as we have already seen. Different servers of this generate short URL service would get a different range so as to avoid collisions. Next, the generate short URL service would then use the counter that it got from the Zookeeper to create a short URL. Let's say it creates tiny.url/000frlb. It would then also save the mapping of this short URL to the original long URL in the URL mappings database, as you can see here. Also, for faster access, the mapping is also saved in the URL mappings cache. Finally, the generated short URL is returned to the client and the process is completed. Let's look at the end-to-end flow for retrieving the long URL from our generated short URL. This is the other side of the picture. First, we have generated the short URL. Now, we want to get our original long URL back from the generated short URL. So let's see how this works step by step. The user first types the generated short URL in the browser. As soon as he hits enter, the browser would send a GET request to the API gateway on the /short URL endpoint. This endpoint is the same thing that the person has typed in their browser. The API gateway would then receive this request and then it would forward to the get long URL service through a load balancer. The get long URL service would then first check the URL mappings cache to see if this short URL to the corresponding long URL entry exists. If it does not, then the cache would check the database and would then fetch the record from the database. Ultimately, it would also update itself so that the future requests could be served from the cache without the need to go to the database. Now, this mechanism that I have described and this part of the diagram effectively, it's a read-through kind of style or a read-through mechanism. Why it is called a read-through mechanism? Because we are reading through the cache. So the system would send the request to the cache and then the cache would read the DB and then also update itself. So effectively we have read through the cache. Finally, the next step, the get long URL service would then send this long URL back to the API gateway. It would then forward it to the user. In this case, it would be www.google.com. Let's now move to the database selection part. Whenever we are deciding the type of the databases, these are some general guidelines to follow. We mainly consider the speed, the scale, the query pattern, and the structure flexibility. It's important to remember that while these guidelines would help, the final choice would still depend on the project's unique needs. Now let's see what do we get for the URL mappings database. First, we need to quickly fetch the long URL for the given generated short URL. Now this we know from our non-functional requirements that any delay can cause user frustration and can slow down the access of the website. Therefore, NoSQL would be a better choice considering the aspect of the speed. Next, let us move to the scale. Now we know that the service will handle millions of URL mappings daily. NoSQL databases can handle this large amount of data more efficiently. Third, we have a simple query pattern that is just reading the long URL mappings using the generated short URL as the key. NoSQL is a good fit here. Therefore, considering these 3 points, we'll go with the NoSQL database. Precisely, we'll use the key value store here. Now let's see how we will model the data in our URL mappings database. We'll also look at some common queries that we need to run on this database and how we can optimize them further. So firstly, we know that from the discussion in the database selection that NoSQL is perfect for this kind of database, given the requirement for our low latency, the scalability, along with a simple query pattern. Now in terms of the structure of our database, it would be in the key value format. The short URL would be the key and the long URL would be the value. The most common operation that we will perform is reading the long URL from a given short URL. So this means we will use the short URL as the key and then use that to find its corresponding long URL. Now to speed things up, we will be indexing on this short URL column. Now what is indexing? Let us understand this with the help of an example. Let's say you have a book. You want to read a chapter. You want to quickly find the content of that chapter to read. What you will do? You'll go to the index page of that book, see the chapter name, see the page number against that chapter, and then quickly go to that page. So that chapter name is like a key. The actual content of the chapter that you're going to read is like the value. And how are you able to quickly find the chapter name? Using the index page. So similar to that, our indexing on the short URL would help us locate the short URL entry quickly, thereby ultimately helping us to find the corresponding long URL faster. Now we have previously explored the flow for fetching the long URL from the generated short URL, that is using the GET request to the /short URL endpoint. But we have missed a significant detail there. The story doesn't just end with returning the long URL to the client. Just returning www.google.com to the browser isn't sufficient. Why? Because the browser needs to take the next step, that is actually open the long URL web page. Now how does that happen? Let's take a look at the diagram once more. The user types in a short URL in the browser. When he presses enter, the browser sends a GET request to the API gateway. The API gateway then receives the request and then forwards it to the GET long URL service via a load balancer. The GET long service checks the cache for the short URL. If it's a cache miss, it would read from the database through the cache. We called it a read-through mechanism, if you can recall. Finally, the GET long URL service returns the long URL to the API gateway, which then ultimately sends it back to the user. Now here's the significant detail that we missed. When the API gateway returns the response to the user, it returns the HTTP status code of 301. Now what is 301? This 301 status code tells the browser to redirect to the long URL. So basically, browser gets the long URL from the response along with this status code. It understands this status code, that is a redirection, and therefore it would actually open the LongURL web page, completing the full process.